Hello students, in today's class we are going to be working on derivatives of a function. So this is the first section of chapter 3. So to start, we're going to do this quick warm-up problem. Again, please pause your screen, try solving this on your own. So hopefully you paused the screen and now you're just coming back to check your answers. Now remember, in order for us to find the slope of a tangent at specific points, we need to use the limit as h approaches 0 for the function f of x plus h minus f of x, all divided by h. So we're going to go ahead and do that now. Oops, this should read 0. So looking at the function, we're going to do x plus h quantity squared minus 3 minus, we're going to put these in brackets, x squared minus 3, like so. So we're going to end up here is, we're going to end up with x squared plus 2xh plus h squared minus 3 minus x squared plus 3, all divided by h. And what you'll notice here is that our x squareds should cancel out, our 3's should cancel out, and you're left with 2xh plus h squared, all divided by h. You'll notice here that the numerator has a common h in common, so 2 times the quantity 2x, or h times the quantity 2x plus h, all divided by h. The h's will cancel out. And then remember, we're looking at this for the limit as x approaches 0 for the function 2x plus h now. So if we substitute the limit here, where h approaches 0, you'll notice that we are left with 2x. So keep in mind, they wanted us to find the slope of the tangent at x equals 2. So all we're going to do now is we're going to replace the 2, and we're going to get 2 times 2. And so the slope of the tangent at x equals 2 for the function is equal to 4. So I hope that helps, and we're going to look at this a little bit more. Now keep in mind, the derivative is going to give us the slope of the tangent. So that's the slope of the tangent for any function. So we've seen it as the following. So we call this f prime, that little apostrophe is f prime of x, is equal to the limit as h approaches 0 for the function f of x plus h minus f of x, all divided by h. We've also seen it with a derivative at a point. So f prime of a equals the limit as h approaches 0 for f of a plus h minus f of a, all divided by h. The big difference between this equation and this one is that this one is a more generic form. I actually like this one a lot better than this one. With this one, you're just substituting that x value immediately. So in the warm-up problem, instead of doing that long workup that we did, instead of putting x, we would put 2. Again, I like the original better because once you have the equation for the slope of a tangent, you could substitute any value you want. This is very specific. So again, you can plug in the value of a at the beginning or at the end. Again, I prefer the end. So here are a couple other forms of the derivative. So f prime of a is equal to the limit as x approaches a for f of x minus f of a equals x divided by a. And we have the following just below it. Big difference here is we're kind of finding the average at some interval h, a little bit above x and a little bit below. So the derivative notation, it is listed and looks like what you're seeing here. F prime of x is the most basic. You'll sometimes see y prime, but a lot of times, especially as we get farther, it's going to be called dy dx. And if you think about it, d stands for delta, which is that little triangle, which means change in y, dy, and dx is change in x. So that's why we can get the slope formula. It's the change in y divided by the change in x, which in algebra was your y2 minus y1, all divided by x2 minus x1. This thing, df divided by dx, is the same thing. It's the derivative of the function with respect to x, and d dx for f of x is the same idea. So let's look at the next slide. We're going to do one of our newer formulas using 4f prime of 4. And notice that we're using one of the newer formulas. So I just wanted to show it to you. Again, it's an alternative form. If you like this one better, you're more than welcome to use it. If we're going to do the same base, we are going to replace your f of x so we have x squared minus 3x minus f of a. So keep in mind f of a is now, let's put these in parentheses, is 4 squared because it was originally x squared minus 3 times x, or minus 3 times 4, all divided by x minus 4 because that's what the formula calls for. We're going to be left with x squared minus 3x minus, now 4 squared is 16, 16 minus 12 is 4, so that's going to be minus 4, all divided by x minus 4. You'll notice that the numerator is factorable, so that is going to be x minus 4, x plus 1, all divided by x minus 4. You'll notice here that the x minus 4's on the numerator and denominator can be cancelled out, and you are left with the limit as x approaches 4 for the function x plus 1. Then we substitute your limit in there. We get 4 plus 1, and that's equal to 5. So f prime of 4 is equal to 5. So the slope of the tangent line at x equals 4 is 5. So a couple things to consider is our derivative vocabulary. So we can say f prime of x. So f is differentiable at x. This is the same as saying f has a derivative at x. Now, a function that is differentiable at every point of its domain is a differentiable equation. So in English, if we have a function that is differentiable everywhere in its domain, then we call it a differentiable function. A function must be continuous in order for it to be differentiable. So if you're having jumps and leaps, then it's not going to be differentiable in that interval or differentiable period. Now, really important that you write this down. These are some of the implications of the first derivative. So one, the first derivative gives us the equation for a slope of the tangent line. So this is not the same thing as the equation for a tangent line. This is the equation to find the slope of a tangent line. 2, it gives us the slope of a tangent line once we find a specific point. 3, it gives the critical points. So the critical points tell us where a graph starts to increase or decrease. So critical points, again, gives us the points where the graph begins to increase or decrease. Increase or decrease. Which helps us find the max or the min. These critical points, they literally tell us the max or the minimum point of the function. So we can sketch it based on the critical points alone. So let's look at some other examples. So going back to a quick example, we're going to find the derivative of 1 divided by x squared. Again, this should be pretty similar. Whichever formula you use, we're going to use the limit as h approaches 0. for f of x plus h minus f of x, all divided by h. We're going to substitute the values in. We're going to get 1 divided by x plus h, quantity squared, minus 1 divided by x squared, all divided by h. So this is what your formula should look like. If we start solving for that denominator, we get 1 divided by, actually, looking at this now, it doesn't make any sense to start factoring that out. Rather, what I'd rather do is start finding a common denominator. You'll notice that in this particular portion, it lacks the x squared on the denominator. So what I'm going to do is I'm going to multiply x squared to the denominator and the numerator. So that's going to give us x squared times x plus h, quantity squared, minus, you'll notice that the denominator here is lacking the x plus h, quantity squared. So that's what we're going to multiply by here. All divided by x squared times quantity x plus h, quantity squared, like so. All divided by h. This is what your equation should look like. You're going to love the rest of this chapter, I promise. It does get easier. So what we're going to have now is x squared minus, I'm going to expand the x plus h quantity squared into x squared plus 2xh plus h squared, all divided by x squared times quantity x plus h, quantity squared, all divided by h, like so. And we are going to, once we simplify the top, x squared minus x squared goes to 0. And then we're going to have negative 2xh minus h squared, all divided by x squared times quantity x plus h, quantity squared, all divided by h, like so. And then we can factor out a negative h from both sides. So negative h times the quantity 2x plus h divided by x squared plus 2 plus h quantity, or x plus h quantity squared, all divided by h again. You'll notice here that I can rewrite this again, taking this h and writing it underneath this function right here. And so it would read negative h times 2x plus h, all divided by h times x squared times x plus h quantity squared, like so. The h's will cancel out. You're left with negative 2x plus h divided by x squared times quantity x plus h, quantity squared. Now, finally, if we substitute 0 in for h like we have been doing, we're going to be left with negative 2x divided by x squared times x squared. You'll notice here that the x on the numerator and the x on the denominator will cancel out, and your final answer should read x divided by 2x cubed. So just to clarify, this x will cancel out with this squared, and then x times x squared is x cubed. And so this is going to be our derivative to find the slope of the tangent line at any point. So I know that one was a little long, but let's keep moving forward. So graphing from f prime from f. So in order for us to do that, we're going to calculate or estimate the slopes for various values of x. We're going to plot the x comma y prime points and then connect the points with a smooth curve for x values where f is smooth and continuous. So I'm not going to exactly show you how to do that just yet. I'm going to give you examples and we're going to work on this in class. But I did want to give you some examples to at least start with. Now, what I'm giving you here is the following function: f of x equals x cubed minus 4x squared plus x plus 6. We're not going to do the long proof to find the derivative. However, I've done it already, and this is what it looks like. It says f prime is equal to 3x squared minus 8x plus 1. What I've gone ahead and done here is I found x equals this, x equals 0.1314, and x equals 0.2535. Now, when we look at that in Desmos, this is what those values give us. So the first value I gave you, 0.1314, that's this value, that's a critical point. So what happens here, and let's go back to this graph really quick. If I took this derivative and I solved it for 0, either using factoring or the quadratic formula, I would be able to solve it and get x equals 0.314 and x equals 2.535. That value is our critical point. So just to reiterate, you take the derivative, you solve it for 0. When you solve it for 0, you get these 2 points. These are our critical points. They tell us when the value starts increasing and decreasing. So at 0.131, this point right here, that means the graph changes. It was originally increasing, as you can see here, but as soon as we got to x equals 0.131, it started decreasing. And then once we got to this other point down here, 0.2535, what that does is it tells us the graph changes again. It goes from decreasing to increasing again. So that's how the critical points help us. So one, they told us when our graph started changing from increasing to decreasing, and vice versa. It also tells us where our local maximum is, which is this. It also tells us where our local minimum is, which is this value. So taking what we know that this value is increasing from negative infinity to 0.1314. And then you'll notice that it starts decreasing from 0.1314 to 2.535 is when it starts decreasing again, because it is a cubic. And then again, it starts increasing at 2.535 to infinity. So that's how we use these critical points to help us determine increasing or decreasing values. So I promised that we'd look at the graphs. Wrong button. So let's take a look at the graphs again. Notice I've pointed at 0.131 at 2.535. If I graph its derivative, this is what it would look like. So notice the blue line. Now remember at 0.131 on the red line, the original graph, if I look at the blue line, its derivative at 0.131, you'll notice that it's equal to 0. So if we take a look at a critical point and then we start graphing its derivative, that's what we want to look at first. We take its maximum and we move it down to where it crosses 0. And then we take a look at this point here, the minimum, and we see where it crosses on the other line. So notice 2.535 also crosses here. So if we start to graph with that, we'll know that this is where it crosses the x-axis. And you'll also notice something else, hopefully. Notice how from negative infinity to 0.131, our graph was increasing. For the derivative, from negative infinity to 0.3131, it starts decreasing here. From 0.131, it started decreasing. And notice that just followed suit. The only time it started changing is after it crossed. So a lot of what you're going to see here is our slopes. So see here that slope is going down, down, down. And once it starts changing, that's when it crosses the x-axis. So I want you guys to notice that when you have a cubic graph, a third power graph, its derivative is going to be a squared graph. It just kind of steps down by one, and so it changes from 3 curves to 2 curves. So let's look at the next example. Again, we're going to work on graphing in class. So again, you must be given at least 1 point, start at your graph at the given point. We'll talk about this. Example 4, same idea. We have x squared minus 6x plus 10. We solve the value here. What this does, this x equals negative 3/2, this tells us what the graph is doing already. We know that this is an x squared graph. What that means here is that it should look like a parabola of some sort. And it's a positive x squared, so we know it's going upwards. So we know from negative infinity to 3/2, it's decreasing. Then we know from 3/2 to infinity, it's increasing. Again, looking at their graphs, this is the original x squared graph. We know that the critical point is here at 3/2, or 1.5. I graphed that wrong. Oh, this should be 2x minus 6, and this will be 3. My apologies. So this should be 3 and 3. I just wrote the wrong number down earlier, so you'll see that it matches what I said earlier. And if we look at its derivative, you'll see that the maximum or the minimum here is now the point where it crosses the x-axis. So let's move forward. Now we have this last thing we're going to look at is one-sided derivatives. So we say that the function is differentiable on a closed interval a and b if it has right-hand derivatives and left-hand derivatives, and everything in between this interval exists. So let's take a look at an example. It's kind of counterintuitive. So if you think about it, if we're looking for a left-hand limit, that means we're looking for the function at -1. Now, if we're coming to look at -1 of this cubic graph, so let's show you this cubic graph really quick. Y equals x cubed. So we're looking at this cubic graph, and we want to look at the interval from -1 to 2. So what we're going to do really quick is I'm going to put some boundaries for us. So we're going from -1 to, I believe I said 2 to 2, like so. Now, if I wanted to look at the limit at -1, so if I'm looking at the limit here at -1, and I'm looking at the limit at 2, well, if I'm looking here at the limit at 1, then I can't really start from the negative side. I have to start from the positive side because I have to go towards it. If I'm looking at the right-hand limit, I need to start going towards the right-hand side because there's no value on the other side because it's a closed interval. So looking at this again, If I'm looking for a left-hand limit, so at -1, we need to come from the positive side. So I'm going to give you the f prime already to save us some time. So this becomes 3x squared. It will be that fast for you soon. Then what we're going to do here is, what's the value of 3 -1 quantity squared? Because we're coming from the positive side. And so that's going to be equal to 3. If we really want to be technical, we need to pick a point that's approaching -1. So we could theoretically put 0.9999 squared. And we'd get something very similar to 3, probably something like 2.99. Looking at the right-hand side derivative, we need to be coming from the left side, or the negative side. So the same thing applies. Your derivative was 3x squared. We're doing 3 times 2 quantity squared. And we're left with 3 times 4, which is equal to 12. Again, if we wanted to be technical, coming from the negative side, we'd pick 3.99. Oh, 1.99 squared, and we'd get something very similar. So this just tells us that they have left and right hand derivatives, which is helpful when we know it's continuous, because if it is continuous, then we know if it's differentiable between an interval a, b, or in this particular case, -1, 2. So the last problem that we're going to look at is a give me, but I wanted to make sure I threw it in there so you didn't start taking derivatives already. We wanted you to find the average rate of change over the interval -1, 4. So notice we asked you for the average rate of change. That means the change in y divided by the change in x. We did not ask you for the average rate of change of a tangent. So in this particular case, you would literally be doing something as basic as f of 4 minus f of -1, all divided by 4 minus -1. So we know that f of 4 is going to be equal to, what's that, 16 times 3, that's 48, minus f of -1 is going to be 3 divided by 5, because 4 minus -1 is 1, positive 1, so that's 5. And then we're going to get 45 divided by 5, and 45 divided by 5, as we all know, is 9. So that's the average rate of change over the interval, -1, 4. In the next video and in class, we are going to be talking about the second derivative, but we'll save that for next time. So that's all for now. I will see you guys next time.